Okay, in the last class we have talked about the metal, but today we will move on to the ceramic. Okay, so when we talk about ceramic, what is the first thing come to your mind when I say ceramic? Arina? What's the first image that come to your mind when I say ceramic? Pottery. Okay, Amirul, if you are if you are going to define ceramic, how do you define that? Something hard. This also hard. Brittle. Okay, and then? As for now. Okay. So to make a classification is not easy because for example, when people say nanomaterial, we know something that is small, but how small is the thing? It's like ceramic lah. Ceramic, if you say hard, this also hard. Metal also kind of hard lah, kind of hard. But the definition of ceramic is like this. It's a compound. Okay, let me put first. Ceramic, the key definition, ceramic. Because for metal, it's easy. Something that have metal element inside it, or for alloy, have more than one metal element. So that's metal. For polymer is also quite easy lah, the definition. Something that chain-like, I mean that you have a monomer and you are repeating again and again, then you get a polymer. But we go for the definition of polymer later on lah. But for ceramic, it's quite diverse. Because ceramic is a compound. We can say it's a compound. The key definition is a compound between metallic and non-metallic. Metallic, that's one key definition. And most frequently is oxide. Oxide meaning that is react with the oxygen oxides. For example, aluminium oxide. For example, aluminium oxide. Okay, so this is aluminium oxide, and then you have also silicon dioxide. Silicon dioxide is sand, pasir. So this is silicon dioxide, and then you have what? You have also silicon carbide oxide. You can have also, so this is Al2, silicon carbide. They frequently oxide, this I not finished. Most frequently they contain oxides or carbides or nitrites. Most frequently lah. Okay, so this thing. So example is aluminum oxide, silicon dioxide, and silicon carbide. And then that's one part. Plus, this is one part. So this one part. Plus what people normally refer as traditional ceramic. Traditional ceramic is basically the ceramic that is made from the clay. Okay, those composed of clay mineral lah. Clay mineral. Basically, clay is not sand. Clay is not silica. This is silicon dioxide is basically sand. The sand over there. Clay is not. Clay is just like this lah. This clay. Apa ni? Clay apa dalam bahasa Melayu? Tanah liat. Tanah liat for haulat. That is clay in Malay. So clay is not silica. It's a lot of mineral inside that. So composed of clay mineral lah. Composed of clay mineral. Example lah, I give you example. Example like porcelain lah. Porcelain, bricks, and so on lah. Bricks, tiles, even these tiles also tiles, and tiles and so on. So that is another definition. Plus something we call, what else? Cement. Cement also under ceramic. plus, another plus also glass. So you can see the ceramic is quite a diverse class. Glass. Apa colour macam ni? So that thing. So this is basically the overview of what is ceramic. When people ask you what is ceramic, you can say there are a lot of things lah. Because ceramic, why they have a lot of distribution like this is because of the bond inside ceramic can be either fully ionic or fully covalent. So the ceramic, this is the bonding inside the ceramic itself lah. We will talk about the bonding in more detail after the raya lah, after the mid semester. But for time being, we say that the ceramic, the bond that makes ceramic can be fully ionic, can be intermediate, mean that it have both ionic and covalent, and or also it can have all the covalent. So ceramic can be here, can be here, can be here, meaning that it can be fully ionic, partially covalent, and fully covalent. In fact, the garam, sodium chloride, your table salt, under this definition is also can be considered as ceramic. Okay, even though it's quite strange to say our table salt is a ceramic, but from the definition, the table salt also under the ceramic. If you look any book, some book they say that the table salt is also under the ceramic. So you can see it's quite what we call quite big, quite diverse in terms of definition, because before you learn something, you need to know about definition. So that is about ceramic. Okay. So this is the definition of ceramic from what we call from definition point of view lah. But you can also define ceramic from the application point of view. For example, let's say you want to define ceramic in terms of classification. So we can have something like this, ceramic. So now I want to define ceramic based on its application rather than this, what to say, this is not application, this is basically a definition lah. I don't know what to say. What is this? It's just definition lah. You know, finding the right word also is difficult. I also don't know how to say in Malay. Ambil apa? Bawah apa? Yeah, you know lah, ceramic is that. But under the application, you can divide ceramic into many parts. Okay, the first part is you can put ceramic under the glass. This in terms of application, you want to see ceramic under the application part. Under the glass, you have normal glass, and also you have glass ceramic or ceramic glass? Glass ceramic. Okay, and then you have also under the what we call under definition clay product. Under application, clay product. Okay, clay product can be something that is structural, either structural. Example for structural clay product is tiles, bricks, and so on lah. Okay, and then that is structural, and then one more. They call it whiteware. Okay. So example for this like porcelain and so on. In fact, the one that you present, I mean some of you present in the, who present ceramic last time? Alif dengan Arina. Okay. So I think Arina said about something about earthenware, something like that lah. So the earthenware, and then stoneware, and then lastly the porcelain. This earthenware and stoneware is basically around here lah. Around here, it's a clay product. Okay. And then after clay product, we have the refractories. Under here, tak entik. Refractories. Refractories, what does it mean by refractories? Meaning that they use it to extract something. Refractories. For example, in the previous class, we learned about the metal, right? In order to melt metal, we need something that can resist the temperature of the melting temperature of the metal lah. You need something to hold that thing. So people use ceramic lah to hold the thing. Okay. So refractories, you can have what we call, you can have either clay base or non-clay lah, non-clay. Okay. Under clay, you have what we call fire clay. So here, I put in this red color lah, fire clay. I just write first. Fire clay, and this is we call it fire clay, and then high alumina. Okay. Later I will discuss this thing. But basically, this is the what people use to put into the kiln. For example, let's say I put where is the thing? I need to open the internet first. Connect the internet. Okay, open this thing, and then KILN. Okay, so for example, when people want to create a kiln, this thing, if you want to melt something that is at very hot temperature, you use a ceramic. So that is refractories. We call it under the refractories. So this thing, the whitish part here, this whitish part here is basically this lah. The clay, either clay or non-clay lah. So that is basically what does it mean by ceramic used in the refractories. And then you can also have the ceramic used in abrasive. Abrasive. This is typically for grinding and so on lah. Later we will discuss a little bit about that. I just put first, and then you have cement. You have cement, and then what you have panjang punya ceramic biomaterial. I put first biomaterial, and then you have carbon. Even carbon, the one that we learned before, like the graphite in your pencil lead, that people also classify under the ceramic. Carbon. Example for carbon is something like, put this, like graphite, diamond, and also fiber. Okay, carbon fiber, and then they have advanced ceramic. Advanced ceramic. Then advanced ceramic. Advanced ceramic. Example for advanced ceramic, the one that normally they use a carbon, like a carbon nanotube and so on lah. Carbon nanotube. Oh, dah habis dah sampai ni. Nanotube. Graphene, the one that I show you last time. Graphene. Fullerene. Tahu tak fullerene apa? Fullerene is something like this. Fullerene is something like this. People call it buckyball. So basically, this under the category of nanomaterial lah. Same like graphene, nanotube, and so on. Nanotube is like a tube. Graphene is like a 2D planar layer. Fullerene like a football. So they have their own use lah. It's like a cage of something, but we will not discuss that thing. But basically, this under the ceramic, this is basically how you not how you define. I mean that the classification of ceramic based on its application. You have 1, 2, 3, 4, 1, 2, 3, 4. You have 8 big classification lah. Okay, so I will not discuss all in detail. We will not discuss. Maybe we focus only glass only lah. Okay, glass Saya tak ada tempat nak tulis dah. Habis dah tempat. Macam mana? Nak guna sana, kamera letak ni. Put here lah. Normally I like to use 2 whiteboard, but what to do? Okay, the glass So the sand glass is made from the sand So the sand is basically what? Sand is basically what we call is a mixture. It's basically sand. The sand, the one that you can see, is basically coming from the stone lah, from the what we call wear and tear of the stone, maybe from the what we call the wind, the wind, and what we call the tide, the wear and tear. You get the sand. So this sand, if you hit it, this sand first. This sand, what is the composition of the sand? Inside the sand, you have this silicon dioxide. Okay, inside the sand is silicon dioxide. So sand, if this silicon dioxide, they arrange regularly, meaning that they have arrangement of silicon dioxide, you got something called quartz. Quartz is basically silicon dioxide that is arranged periodically. They have like regular arrangement of silicon dioxide inside the sand itself. That's why when you see the sand close up, sand close up, sand close up, you will see something like that. Okay, tak close up sangat ni. So there is sand. So basically, if you look here, if you take any sand, sometimes you will see a very like white, very transparent, something very clear and very, we call it crystal like quartz lah. So this thing, some of it is a crystal like. It's like the crystal that I showed you before. This also made of quartz lah, but this is more more elaborate quartz. This is basically coming from sand lah. It's quartz. The sand that you found is just a small size of quartz. Normally you find something like this lah, small size. This like regular arrangement. Because if the thing is not crystal, you don't see something like very sharp edge like this. You will see something like just block like that. Okay. The reason why you have a sharp edge because the molecule sort of like arranged very periodically in certain angle and so on. That's why you get the sharp edge and so on. Okay, so this you have sand and you have this what we call quartz. Okay, if you try to hit either sand or quartz high enough, this thing will be melt. Okay, if you hit it high enough with a high temperature enough, what will happen is that the atom in the silicon dioxide will vibrate. Okay, will vibrate. Because the heat, the idea of giving heat is basically simply to make the molecule jiggling around, vibrate. So at a certain point, the vibration is strong enough to the point that the bond is break. So this is what we call melting point lah. When you vibrate a solid high enough to the point that the atom break the bond, we call it melting point lah. So until it melt, call it melting point. So you get a gooey liquid silicon dioxide. Okay. And then if this thing cool down, you get what we call glass lah. You get glass. So you can try lah. Take sand, hit it until it's hot enough, and then you cool down, you get glass. Okay, but one of the I want to talk about what happened here. What happened here during this thing, during this part. During this part, I want to talk about here because this is what makes this sand different than the ice. Because water, water ice, you can also have ice. You can melt, and then you melt, and then you cool again. You get ice again, right? You get ice again. So ice like this. Ice. Ice, and then melt, hot, melt, and then you get ice. So this for water. Okay, now we want to see the difference between what is different between this and this. Okay, the silicon dioxide, if you look under the microscope, not under the microscope, the silicon dioxide, the original silicon dioxide or quartz, they are very, the molecule is very arranged in nature lah. So let's say I have this, let's say I put like this lah. Can you see at the back? Misak on misak. Nampak? Okay, nanti dulu. Macam mana saya nak lukis ni? Tak tahu lah nak lukis macam ni. Ya, I just draw lah, whatever this thing. Okay, so let's say I have red, and then red here, and then red here, and then red here, and then red here. So now this is what we call a periodic arrangement. Okay, periodic arrangement doesn't necessarily mean the atom just like this. Okay, periodic. When I say periodic arrangement, it doesn't mean like this only. This is one of the type of the periodic arrangement, meaning that the atom have the pattern. So the pattern here, one atom. But of course, this also the pattern. For example, if the atom is here, in the vertex here, if it's arranged like that, in the what we call, this is what we call also periodic arrangement. This, same like this. Okay. Something like that. Okay, so this also periodic arrangement. If you have something like what we call like this, like graphene or whatever that thing, that also periodic arrangement, because now the atom here, let's say I draw atom in red, is arranged in such a pattern lah. So definition of crystal is like this. So long that you have a pattern in repeating in the lattice, then we call it is a crystal lah. So like that. Okay. So this repeating, the pattern repeating like this lah. This is also repeating. So this is basically silicon dioxide. When you hit this thing, what happens? This ball is break. The difference between when you hit the sand and when you hit the water is that when it's cooled down, the sand don't remember this configuration again, as if they forget this thing. So when it's cooled down, let's say you hit this thing, when it's cooled down, can you see or not? Siapa nama belakang tu? Syamimi, nampak tak? Buat nampak lah ya. When it's cooled down, you have something like this. Something like what we call chaotic arrangement of the atom inside the molecule. So at first you have something like this. So you have sort of like some pattern lah. You got some pattern, repeating pattern lah. Sort of repeating pattern. I don't draw it carefully, but basically you get the idea. You get the repeating pattern of that. It's not nice drawing, but at least you get the idea lah. But once you cool, you get something like this. It's chaotic. So for the water, it's different. For water, you can heat the ice, get the water, and then cool it again, you get the ice again. Because during the cooling, the water molecule will try to rearrange themselves. They remember how to arrange themselves, and then that's why you get ice, the snowflake, and so on. You get this arrangement of the water crystal lah. But for the sand, it's different. When you cool down, it doesn't remember the original state, the structure. So when the temperature become lower and lower, it's much harder for this molecule to move around. So now at the end, you get something that is solid. You get something that is solid, but have the molecular structure of the liquid. But have molecular structure of liquid. So this is basically what makes sand different than the water or whatever else lah. So so when you heat this thing and then you cool down, you get glass. At this point, you might say that, okay, making the glass is very easy. Just take the sand and then heat it, and then you get glass. But when you do some like that, when you just take a sand and try to heat it, you get the glass, but you end up the glass that is not really usable lah. That is not similar like the glass that you see in the life lah. Because the glass that you will get is full of impurities. Okay, you get something like maybe like early glass. Ini semua cantik. Impurity glass. Ini semua beautiful glass. If you try to make a sand, if you try to just heat up the sand, the normal sand, you cannot get something like this, because in order to get something like this, you need to have a right combination. Most of the sand that you found doesn't have a right combination of mineral in order for you to make this transparent glass. Because there are two things in order to make this, in order to make a clear glass. Okay, in order to make a clear glass or whatever, clear glass or usable glass, you need two things. You need right combination of mineral, and also high temperature. Usually, in order to melt the sand, you need a temperature roughly around 1200 Celsius. Okay, roughly like that. So this temperature is not common in the normal fire lah, because fire, if you make a fireplace, for example, let's say I have the wood and I make a fire. I have a wood and then I make a fire there. The temperature for this fire typically around 600 to 800 Celsius. Okay, typical temperature. Of course, on the candle, the temperature is much higher lah. On the candle, the temperature, the hottest part here can go to 1000 to 1200 Celsius. Okay, if you have Bunsen burner, let's say you have Bunsen burner in the lab, the one that gives you the blue flame, okay, the blue flame thing, that can go to what we call up to 1400 Celsius. You might say, okay, this is 1400. Why not? We can use it for this making the glass. Because we need to remember this thing, Bunsen burner here, they use propane. This candle, they use this wax. If you want to make a glass at large industrial scale, you cannot just use a candle or this thing. You need a lot of wax. You need a lot of propane, which is not industrial friendly lah. So normally people, and imagine long time ago, the early civilization, they don't have all these things. They don't have this gas. They cannot, what we call, extract this gas. They don't have this wax. They have wax, but they don't have like right combination of wax lah. So they have only this thing. And also this thing is much more useful to convert into the large scale lah, because you can just burn the wood and so on. So the idea when we said that to make a clear glass you need high temperature at 1200, what does it mean is that to use something that is common and get that temperature. Of course, you can get that temperature using the Bunsen burner, but the Bunsen burner is only just small flame. The surface area is so low, so if you want to make a big industry, you cannot lah. So that's why, what does it mean by high temperature lah? Okay, so right combination of mineral. You need silica dioxide and other stuff lah. Later I will talk about the stuff what they put inside the glass lah. So the high temperature here, they need 120,000 Celsius. So there are occasions that you can see this glass, what we call, occur naturally in nature when there are lightning, because when you have a lightning, pete, lightning, okay, and then lightning happen in the desert. Desert is full of sand, right? Desert. So if you have lightning on the desert, then this lightning is hot enough because the temperature of the lightning typically around 10,000 Celsius lah, roughly like that lah, 10,000 Celsius like that. If we, what we call, let me check. Lightning temperature, kau tak saya cakap je. Lightning temperature, is it correct? Apa ni? Oil. Lightning. Apa? Lightning, alamak. Tukarlah dalam Celsius. But it's 30,000, much more higher lah, 30,000 Celsius. 30,000 degrees Celsius. So this temperature is far beyond the melting point of the sand, silicon dioxide. So you will assume that if the lightning happen in the desert is full of the sand, you will get the glass, which is true lah. So you can find the glass in the desert. They call it, penuh, nanti saya akan padam ni. They call it this. They call it fulgurite. Fulgurite. So I show you here, fulgurite. So that is image of fulgurite. Blah 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 blah. My image. So that is basically the glass. This is basically the glass lah. Glass. So the outside is quite coarse, it's quite rough, but the inside is like a glass. The inside because it's hollow. It's hollow. Inside this is hollow. You see, they are hollow there. Inside that is like a glass like. The outside is full of the sand lah, because the temperature when the lightning strike on the glass, the inner, if you have this thing, for example, this part, let's say this is the sand, this is the sand. The lightning strike, this part become very hot, but over here is less hot. So that's why the glass is fully fused here. So if you can look inside the hole there, it's very smooth lah. But the outside, because the temperature is not what we call, not very high as here, so you get gradient of temperature gradient lah. So that's why on the outside it become like coarse like that. So inside it is hollow. If you see inside, it's like a glass. So this nature occurrence to show you that the glass is indeed come from the from the sand. Okay, I need to rub everything because it's quite difficult for me to work because it's full here. Okay, we want to talk now about the. I will just padam ya, padam atas. Okay, it's full So the key thing that you need to take away from here is that the glass, what happened for the molecule, because this is chemistry also, what happened to the molecule inside the silicon dioxide molecule when you heat and cool. So that's a key point. The molecule doesn't remember their what we call their original lattice, their original crystal structure, and then you end up with a solid but having this chaotic structure of liquid inside that thing. You also learn here that the problem with making the glass is these two things, to find the right combination of mineral, and also you need high temperature. Especially you need to go up to 1200 Celsius, and you also learn about that in the nature also it's happened. When you have the lightning striking on the desert full of the sand, you get the fulgurite, and fulgurite is glass. So let me close this thing first. Close pula, padam. Okay, let me close this thing. Okay. So because the temperature to make a glass is very high, I mean at industrial level, you need 1000 Celsius. What people do is that they add flux. So glass, when we talk about glass, the normal glass typically composed of silicon dioxide. We learned this thing before. Sand, this sand, typical thing. And then they have typical constituent of the glass. You have sand. Basically, this make the majority of glass, sand. And then you have, let me put here, sand, which is silicon dioxide. And then you have soda. Soda is this thing, so, soda oxide, soda lah. And then you have lime, this KAO, and then plus other stuff lah. But these three is major thing lah to make a glass. You have sand, soda, and lime, like that, more or less like that lah. So the main ingredient, where is the thing? So the main ingredient is this. This is main ingredient. Main ingredient. This is what we call flux. The rest is mostly they call it flux. This thing and this thing plus other stuff, we call it flux. F-L-U-K. The purpose of the flux is to reduce. One of the purpose of the flux, to reduce the melting point. The melting point of this melting lah. To reduce the melting point of that lah. Okay, because when you have two things impure, okay, if let's say you have A, okay, let's say A, the temperature of the melting point of A is basically 100. Let's say 200 Celsius. And then B, let's say the melting point of the B is basically 300. Melting point, what does it mean by melting point? Is the range where when you hit something, the melting point, what is melting point? Melting point is basically when the solid start to liquefy until it fully fully liquidized. Meaning that when you put something inside the, let's say, tube, and then you put a solid there. Let's say you put a solid there. Let's say your garam, your table salt inside the tube, and then you try to hit this thing. Once you see this garam, this whatever, this, banyak sangat lah colour saya. Once you see this start to melt, for example, let's say I draw this thing. Okay. Once you see it start to melt, I can copy paste lah. When you see it start to melt, let's say you see something starting to melt, and then it reach the temperature, senang nak guna multiple ni. Until it fully melt, colour lain pula. Until it fully melt like this, this is what we call melting point. This is what we call melting point. So melting point normally is a range. It's not like a one sharp point. Okay, typically melting point is a range. For example, let's say it's melt at 200, and it's totally melt at 202 Celsius. Okay, 202 Celsius. So we can say the melting point for this substance is 200. The melting point is basically 200 to 202 Celsius. The more pure a substance is, the sharper, the narrower the gap, the gap here. Okay. If you mix two things, let's say you make these two things, you make these two different, different compound together. Even though this A have the melting point as, let's say, 200 plus like that, plus minus, and B have melting point 300 plus like that, when you mix two together and then you repeat again this, but now you have the mixture, instead of only one, now you have you have mixture with the green one, you mixture this thing. What will happen is that the melting point that you will see is far down than this 2. Maybe you will get the melting point around 100, something like that. Okay, so this is how people check, how people use melting point as a way, as a tool to check whether a compound is pure or not. The pure compound normally have very sharp melting point. Sharp means that narrower gap. Impure material normally is combination of 2 different material, and when 2 different material combine, their melting point will be far below than these 2. Okay, in lab 1 later on, in next semester, you will go for lab 1. In the lab 1, you will go and do this thing in the lab. You take a powder, pure powder, another pure powder, check their melting point, and then combine them like this. And then you will see that when you combine these 2 things, it becomes impure, and then the melting point suddenly become very low. Not only very low, it's also become, the gap become very big. For example, let's say the melting point here from this, maybe 90 to 150 like that. So it's become lower than this, and also the gap between these 2 is what we call, is larger lah, it's bigger, it's broader. So that is the idea. Okay, so that's why people put soda and lime as a flux. Okay, they can put anything, other thing also lah, like potash. Sometimes people put potash, soda ash. Soda ash is basically how early civilization find this thing is that basically how they do it, they try to find any plant, the specific plant, because remember when you grow something, whatever this thing, and then the root of this thing, they will absorb mineral from the soil, right? From the soil. So the mineral from the soil will go to this plant. So how early civilization make a soda ash to add with the sand during the melting is that they take this thing and then they burn it. And then they filter, they burn, and then they add water, and then they get lah. They have the way lah how to. They burn this thing, and then you get something black charcoal, and then they add water, and then they filter it. They filter this thing, filter. So what coming out is basically having soda lah. Soda is sodium lah. Soda inside that. Okay. So this is what how early civilization does lah. But nowadays, people know that this thing can be taken from this limestone lah. Limestone is batu kapur. Limestone. Nowadays, people just go and take limestone and put the thing. Limestone. Nampak je. Ni limestone. They take batu kapur. So inside this also they have calcium carbonate and so on lah. Okay, so that is calcium carbonate lime coming from here lah. Batu cave yang nampak tu penuh limestone lah. So that's the thing. Okay, so this how the early civilization did the stuff. They found that by burning this thing, you can get the sodium after extraction. Because this thing, you need the pure one. So when they do like this, when they filter this thing, they get the pure one. Okay, so this is the flux. The purpose of the flux is to reduce the melting point so that you can burn, you can fire this sand at lower temperature. So that's the idea for this thing lah. The idea for that thing. Okay. So in order to get sodium, you need to find the plant that is what we call, that is plant grown on sodium-rich soil. Okay, so this is what people do before. They find plant grown in sodium-rich soil, and then they burn this thing. They get the they add water. They get the filtrate contain the sodium lah, and then they add to this thing. Okay. Okay, done lah. So that is how the composition of glass lah. So for there are two types. I will discuss two types of glass that is typical lah. So the first one is soda lime glass. So basically soda lime glass is basically the glass that composed of this thing. Majority is silicon. Normally 70% is silicon dioxide. That what we call the sand. They plus around 16% lime, CaO. Ya ke? Itulah. NO2 lah, NO2. NO2O and plus 5% lime with that CaO. So this is a recipe for making a soda lime glass. Soda lime glass is a glass that you find that making this windows and also the bottle, the drink bottles and typical glass lah, normal glass. Soda lime glass is a typical glass. So let me put example lah. Example, windows glass, windows pane, bottle. So that's what we call a soda lime glass. They have that thing, and sometimes they add also other stuff like potash, magnesium, alumina, like that lah, and so on lah. So it's like a recipe lah. But the main thing is that soda lime glass have 70% the sand, 60% this soda, and 5% silicon glass. This soda lime glass, the properties for the soda lime glass is that it's inexpensive, and also, but it's less durable, meaning that it's break easily lah. It's break easily. So that about it's have less durable, poor durability lah. Poor durability, and also have lower thermal resistance. What does it mean by lower thermal resistance? Is that this glass have high. What does it mean by this lower thermal resistance? This glass have high coefficient of thermal expansion. What does it mean is that if you have a bottle, for example, let's say this, you have a bottle like this. Okay, you have a glass, and then you put this on the hot water, and then suddenly you take it out and put in the ice. It will crack. So that's basically have a high, and then you put this thing into the into this jug, into the ice, into ice water. So basically it will crack lah. It will crack. The reason why it's cracked is because it have high coefficient of thermal expansion. What does it mean by high thermal expansion? Meaning that this thing, normally glass thing, when we hot it will expand. When it's cool it will contract, right? So if you have something that has high thermal expansion, when it's hot it become like this. Cool it become like this. So meaning that the expansion and then contraction is too pronounced. Meaning that if you have something like this happen again and again, it will sort of like compromise the structure itself, because it expand too big and it's contract too big. So the stress happening again and again. If you have lower thermal expansion, it just expand a little bit and then close a little bit. So it's not enough to what we call to break the thing. So soda lime glass, they have poor durability and lower thermal resistance. Lower thermal resistance here mean that it have high coefficient of thermal expansion and contraction lah. So that's the thing. So this is soda lime glass. So example of soda lime glass is this lah, microscope slide. This thing, it's very easily break lah. It's very easily break, but I don't want to break because it will shatter. One of the properties of the glass, it's isotropic, but we come to that later lah. But this example of soda lime glass, microscope slide. Okay, so It's cheap. This is RM1. I think RM1. I think RM5 or RM1 the entire box. Okay, but it's less durable. If I drop this thing, it will break just like that. Okay. There are another type of the glass that I want to discuss today. Where to put? Full. So another type of the glass. So I hope you can see lah. I put here. So I put here. So another type of glass is, we call it borosilicate glass. Borosilicate glass. Okay, there are many types of glass, but I want to focus two only lah. The most common, the soda lime and borosilicate glass. The borosilicate glass, as the name implies, they have boron. Boron. They have boron. So basically, they have the composition. The composition, let's say I put composition. They have around 80% silicon dioxide. 80% silicon dioxide. 13%, usually lah, 13% boron oxide lah, boric oxide. Boric oxide. Okay, the what we call the formula is B2O3 like that. Okay, so boric oxide, and then the rest is just addition lah, and then they have potash plus blah blah blah. So when I say blah 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 here, it depends on whatever that you want to put lah. Alumina is like a trace mineral only. The main ingredient is these two things. The silicon, what we call silicon dioxide and boric oxide. Okay, this boric oxide also help to reduce help to become like the what we call the flux for this melting process lah. But because they put the boric oxide, they have also this glass also have certain properties that is not shared by this soda lime glass. The most important thing, let me put example of borosilicate. Example of borosilicate is lab glass. Labware. Example, labware glass. Okay, contoh macam saya punya ni lab, mana lab? Ni. If you go to the lab, have you ever go to the lab? No? Not yet. So normally in the lab they use borosilicate glass. Sometimes you can see on the label they put it borosilicate. Okay, sometimes. Okay, borosilicate glass. The difference between this and this is that this thing have lower coefficient of thermal expansion. But let me finish this first. Example, labware glass, and then pyrite. Pyrite, the one in your kitchen. The one in your kitchen, pyrite. That's why pyrite you can put in the oven and so on, let's say whatever. So that's pyrite. So this, the properties for this borosilicate glass is that it is a little bit expensive. Okay, it's let me put here kitchenware lah. Kitchenware. Normally kitchenware lah. Kitchenware. They have what we call, they are more durable. Let me put in. They are more durable, and also they have lower thermal, lower coefficient of thermal expansion. As I said, when you hit this thing, when you try to put bangsa benda on this, it just expand a little bit only, and then when you put in the ice, it just contract a little bit. So because of that, not so pronounced, they doesn't stress this glass too much. That's why at the end you get this better thermal resistance lah. So either word we can say better thermal resistance lah. In other word, better thermal shock resistance. Thermal shock resistant. Okay. Okay. So that is basically two type of the glass that you see now. So you learn now the composition of glass. So we focus two things. There are many more, but we just focus in these two lah. Soda lime glass and borosilicate glass. Here, I just cover a little bit here. The glass ceramic is basically, we know glass is a non-crystalline. We draw a picture here. The glass, the way how people make glass is that something that is crystal, like a quartz, silicon dioxide, they heat it, the crystal doesn't have memory to remember what their, what you call the original crystal formation, so you end up with something that is non-crystalline. We call it amorphous. What you call the opposite of crystalline, the opposite is basically amorphous. Amorphous. Okay, so the glass is amorphous, means that non-crystalline lah. So this is the opposite for crystalline. Okay, so the glass here typically amorphous. Amorphous. There are no odor. The molecule inside the glass is just chaotic, like inside the what you call inside the water. The molecule just go here and there. It just is solid lah. It's frozen in time. So glass ceramic, they are a little bit different. They have some crystal. They have some crystal. They have some crystal in it. So meaning that if you look under the microscope, let's say you have this is let's say this glass, you have all this thing amorphous. Suddenly you have something like it's like a crystal here, like a crystal here. Crystal. The definition of crystal is something that have a periodic arrangement. So you get something that is sharp and sharp edge and whatever. So somehow you have the crystal here, like that. Mostly it's amorphous, but they are crystal. So this is glass ceramic. Okay, they have the glass and ceramic properties lah. They have some crystal in it. How they do it? How they create glass ceramic is basically first they make glass. They make glass as usual. Making glass is just simply heating the sand and all the stuff. You get the glass, liquid glass. So you get the liquid glass, making glass. Okay, so you get the glass. So basically you make glass just heat up like this. You get glass. So then they cool it down. So you get a glass now. And then they heat again. This is how they make this glass ceramic. The second step is that they reheat. They make glass and then they cool down. And then the second step they reheat and then they add nucleating. Faham tak saya punya tulisan ni? Farah ke siapa namanya? Fazlin. Farah ke Fazlin? Dua-dua. Reheat nucleating agent. Okay, nucleating agent. What is nucleating agent? In order to make a crystal, you need something to crystal to grow on. It's like when you want to make a nucleating agent. Let me draw. Can I have that thing? Nucleating crystal. Nucleating crystal. Nucleating. Nucleating. Tak cantik lah ni. Tak gambar cantik. Nucleating growth. Ice growth. Tak ada gambar lah. What is picture? Hai. No, tak cantik. In bottle. Susah lah. Tak ada gambar lah. The idea is this. In order to make crystal, you need the crystal to start to grow. That's why if you have pure water, you cannot get a crystal. If you have pure water, you put in the freezer, it will not it will not freeze. Pure water, very pure water, you put in freezer, it will not freeze. But if let's say you take it out and then you try to goncang dia, you shake it, and then you will see the crystal will form, because the act of shaking it create the what we call the promote the nucleation of the crystal. Okay, the snow that you can see happen is because when the snow coming down, it meet with the dust or whatever in the air. So that's why that dust become sort of like, you have a dust here, and then the ice crystal can sort of like latch to this. The ice crystal attach to this, and then because of that, because they have stuck here, and then another kawan dia, his friend come here, and then it become bigger lah. So that's nucleating. They need something to promote the crystallization to happen. Okay, tak puas hati lah sekejap. Crystallization. So okay lah, later lah kot. I think for example maybe here. Yeah, this not really nice picture of that. The idea is this: if you have, for example, let's say you have like a salt, you dissolve the salt, for example NaCl, salt, table salt, and then you dissolve, and then you put like what you call the wire here, and then you put like a paper clip here. You will see that, let's say this paper clip in the middle. When it's cooled down, this is a hot salt. When it's cooled down, you will see the crystal will grow here, So the paper clip become the nucleating agent. So in this case, you can find in YouTube lah. Anyway, so the glass ceramic, they add nucleating agent, typically titanium dioxide. Okay, this nucleating agent will sort of like create this, the crystal inside the amorphous region like that, and then you get glass ceramic. The advantage of glass ceramic is that it heat resistant lah. Of course, most of the glass is heat resistant, but this is more heat resistant lah. Heat resistant is better lah. Pyrite is also okay, but this also good heat resistant. Example for this is, where is my green? Example of this is Example is Corningware. You know what is Corningware? Ain, you know? Masak kat rumah? Masak? Corningware, I mean, certain, maybe if I put Corningware, typically lah, sister know lah, something like this. This is namanya Corningware. If you look at the back, they call it Corningware. So Corningware is name of place. They are Corning is a place in America. They call it the glass capital of the world. The pyrite, Corningware, Corel, coming from the Corning capital. I mean in the US lah. So this you can put it in the oven. You can put it in. You can use it to bake. I mean that you can put it in the freezer. You take this. You can put it in freezer. It doesn't crack. Normally glass you put in freezer, it crack lah, because the ice will expand and crack the thing. So this is Corningware lah. So this is type of what we call glass ceramic. So okay. So this is glass ceramic. So I think we stop until now. So we recap. Today we talk about the glass, definition of a glass, and also what we call the application. We categorize the glass according to its application. We see the behavior of the silicon dioxide when it's heating up. When we heat it and then we cool it, the silicon dioxide will not go back to its original crystal structure, and then you get glass. And then we see also the type of glass, soda lime, borosilicate glass, and we know what is flux. And then at the end we learn about this, what is different between glass ceramic, and so on lah. So maybe we will go in further detail later on, but for now that's it.